hopefully that'll give you enough time to think about it. You should have everything you need to do the assignment ahead. So at this point. And then next week, Monday, we also start the last kind of topic section in the class on graph analysis. And we're going to start with some lecture on like some background in so like in Markov chains. So who's heard of a Markov chain before? Okay. So there are typically two ways that Markov chains are taught. And you often learn one way or the other. I'm going to kind of go over both ways. So usually I find that even if you've seen them before, you will see something new in this lecture because you usually expose to only one side of the world. And then this will be kind of a key basis for understanding PageRank and then some of the other stuff we're doing as well. So it'll be kind of, I think it really is an important foundation for stuff you've seen before. And we'll see some algorithms how to do some stuff just with Markov chains as well. All right. So we're talking today about privacy. And so, you know, this is something that, and in particular, the privacy around like data, right? So most of you probably use so some form of like a social network, right? Is there anyone who's not on any social networks and also wants to raise their hand to claim they're not? No? yeah. So like I don't have an account on Facebook, but I'm on other social networks, right? So maybe that decision was wise for me. I missed out on some friend connections, I guess, but maybe now you realize that like the data on there, you may think you're only sharing with your friends, but it's available to other people, right? So these companies, Facebook, Google, Twitter, kind of any of these, you know, so even Microsoft has like a dozen like social networks that it's creating and trying to build all the time. You know, this data is very useful because it allows them to do this very targeted advertising, right? So I saw this talk a week or two ago, so by Chris Wiggins, and he showed this plot about print advertising. It was like 1990 through about 2000, let's say 2020, and this is money spent on ads. And so you had something, and it's like in the billions of dollars, right? And so you have some chart that will kind of like print, and this was like newspapers and magazines, and then you can look at also the chart for Google and then for Facebook, and so something like Google and Facebook have basically eaten all of the money that used to go towards, I think it was not just print, but also so like TV was similar, like on broadcast TV. So these print and TV, they were just kind of fairly, without really knowing what was effective, showing these ads and selling these ads for lots of money. And somewhere in the early 2000s, this is probably, the dates are probably wrong in here, but at some point, Google, and it's much sharper, but Google and Facebook just took off and ate up all this advertising money. And it's because they have all this data on you, and they can target advertisements, and then they can test, also they can test whether they're effective. They can test whether you clicked on something, and then downstream, the companies, they'll link with them and see whether you actually bought something, right? And so they know what's effective, and they're using your data, right? So there's all this information about, there's data that you have out there, there's health records, there's all sorts of stuff. How worried should we be about the privacy of this data, right? And so I want you kind of to think about this as, you know, what we've been thinking in this class is, is a data set, right? And then you can do stuff with it. You can find, you know, clusters. You can do regression. You can classify. This is in the This is taught in the machine learning class. You can do all this cool stuff with the data, and from the company's perspective, you know, this is helping them earn money, right? In some way. But I want you to think about it in case for some data point, you know, this is so you, right? So if you are one of these data points, do you want a company, or do you want an advertiser, or do you want a government, or do you want some other country to know something about what's in what's in your data, right? But these companies only exist. Google and Facebook are these huge profitable companies because they can turn your data into advertising dollars, right? So they can't, you know, it's not feasible for them to exist and provide kind of a lot of the services that they provide without being able to somehow mine your data. It takes away from this advantage they had over print and TV, and it's what caused all this money, right? So how can we do all this without kind of doing something nefarious for you as the data point, something that you would not be happy about? Okay, and so the answer is, in a lot of cases, okay, they're doing stuff that could expose your data. Okay, there's this, there's like, as soon as these companies started collecting all this data, there were researchers, people like me from like universities, and said, cool, I want to study stuff on this data. There's this cool data set. You want to do class projects on it, right? You want to learn and experience this so you can then go to a company and say, look, I worked on this data, hire me, I can do the same thing on yours. Okay, but then Facebook and Google wants, you know, they're getting backlash if they share the data. You've probably heard in the news that Facebook has these partnerships with people in academia and Twitter, and like I've done this in the past where you can get access to data if you promise to only use it for academic purposes, right? And so that's kind of been the agreement. Apparently some people have violated this agreement. But so is there a better way? Okay, so this lecture will kind of walk through the history of the back and forth of releasing data for good, for studying things that's money, but it's not always about money. There's also some stuff where the output is like science. This medical health records, I want to predict what sort of environmental factors cause cancer, right? If I do that, I need to have lots of data about environmental stuff. And so it's tricky to get that without violating individual privacy in this. Or I want to, you know, so like there's also these scientific questions which are, okay, you know, maybe you could argue that the Google and Facebook are good, you know, you can make that argument, but it's hard to argue that certain scientific discoveries like this aren't good, right? And that also requires having a lot of data when the data point might be you. Okay, so this lecture I want you to think about, you know, if you're this data point, what would you feel comfortable sharing your data in this case? Okay. Yeah.
This might come in like later, but so there is definitely research being done on data, like as you said, like environmental factors and like cancer research, etc. But like diverging medical records is almost certainly illegal, right? So like how do people obtain those data sets?
So sure, right. This is a great question. So in like the medical domain, they've been dealing with this for much longer, and so they have these protocols under which what ways can you release data, and there are certain data sets which are collected that you can get access to as an academic, where you have to fill out a license and get an agreement, and sometimes this can take months to process. But under these agreements, you can often look at these things, and often people need to opt into this. You can add more to that, but.
Could these issues be like circumvented by making everything anonymous, like just anonymizing?
So we'll talk about this. And so one thing they do is they do something like anonymizing this data, and we'll talk about how effective this is. So these privacy approaches are attempts to allow you to still do data mining on the data, but while making individual parts of it still anonymous. Okay, and sometimes you can kind of do this, but there's some challenges, and we'll kind of talk through this. I'll mention one more thing about your question. There's something on campus, a really cool data set called the Utah Population Database. Okay, and so it's run on campus. So Ken Smith is the director of this, and he's trying to create a class that you could take as students, where you could go through a quick license and then learn how to use this data set. And this might come online as early as next fall. If I see it, I'll make an announcement out to some list about it. So that's something to look for. But they have this special thing about a directive from the state of Utah from like 30, 40 years ago, where they were instructed to collect a bunch of this data for the use of making the health better in the state of Utah. So it's kind of I think you can opt out of it, but by default, if you are in Utah, your health records go into this, and this is part of the state. It's like an executive order from the governor from like 30, 40 years ago. And so they have a huge amount of data, but they're very protective about how you can use it, who can use it, and so there's lots of these kind of disclosure forms you have to go through in order to get access to this, do research projects on it. But it allows you to answer some of these questions, but you know, they put some safeguards around it. Yeah?
Could we add in defense?
So defense, sure. Yeah, so you can think of like national defense, you're thinking, right? Say national. Yeah, so you could think of like the NSA, right? Also tied to Utah, they have their big data center is in Utah, if you don't know, and so they it seems to be that that they are collecting lots of data and storing it and processing it, and they're doing this for the purpose of preventing something from going out, right? And so NSA just kind of doesn't release this data. Internal to NSA, I believe, they can analyze anything that they're able to collect. Now, FBI can, for instance, can go and ask to access that data, and I think if they get a court order, then they can get it and see it, right? There's not kind of, they're just doing this by having someone who's an adult in the room, or like a judge or someone who says it's okay to collect this data, and then by kind of the classification level of the data is protected that way. So that's kind of a separate sort of issue here. They're using kind of like only those in charge can use the data, and in the same way inside of Google and Facebook, internally they kind of do some very loose anonymization, but otherwise they more or less, and sometimes they segment it in different populations. Like they only use the data inside Gmail for doing ads inside of Gmail. They don't allow to port that to your search history. So there's supposed to be some barriers inside of Google in that way, but inside those divisions, they're essentially look at that data up to some very simple anonymization, like they take your name off of it. Taking your name off of it does not do a lot of anonymization as well. If you just know, if you look at, you know, if you write your name at the bottom of a lot of your emails, so you can often figure out who it is. If you have an account on Google, who here has never searched for their own name in Google? Never, right? Okay. So almost everyone, not everyone, but almost everyone searches for their own name in Google. Okay. So it's a reasonable thing to do, but if you have your search history, you kind of they're probably one of those people whose names they search for, right? And you can figure out the rest, not too hard. Okay. So So let's talk about, okay, I want to start with a story, okay, it's about health records, okay? And so, let's see, so in around 2000, so there was the state of Massachusetts, I think the governor decided that in an effort to kind of improve understanding of health, right, the health of the state, that they were going to release all of the state employees, their medical records in some database. Okay? So they wanted to be able to release them to researchers to study them and understand some of these kind of environmental health factors and other health factors as we discussed. But they said, okay, we're going to anonymize them. We're going to wipe all IDs, all names, like social security numbers, take that out. But they kept in things for environmental factors and like the zip codes, the birthday, although maybe not the birth year, but I'm not sure about this, and the gender, right? Or maybe it was the birth year, they wanted to know the age, they wanted to know roughly where you live, and the gender seemed important, right? So they kept that in. It was declared anonymized by the state government. They're like, this is going to be a really good thing, right? And so then, but also at that time, Massachusetts and most places, something is like this. You can buy the voter data of the state. I think at the time it was cost $20, and you would get the voter data, which had everyone's names, but also their birthday, their zip code. It says birthday twice, but the birthday and the gender of all of the voters. Not sure if the gender was on there, but there was, like, you could see the birthday and the zip code are in both of these data sets. Okay, and okay, so like you could, so it turned out is there was a graduate student, so at UMass Amherst, so LaTanya Sweeney, who combined these two data sets and was able to identify based on the zip code and the year and government employees, that the health records of the governor of Massachusetts, the person who decided it was a good idea to release these. And the story is, I'm not sure if this is true, but that she mailed him his own health records as a way to demonstrate that this might be a bad idea. And I think that kind of got his attention. And so then Dr. Sweeney now teaches at Harvard. So she kind of built her career around this, but also other kind of important issues about privacy of data, right? So kind of the key thing that's going on here is that you can think you're anonymizing a data set, but there are these other factors which you can use this to kind of de-anonymize it. Kind of this basic anonymization of just wiping out the name. Often, they're kind of the classic way to do this is you combine it with another data set which is out there, and then you can match up names with the traits of the person. Or it could be something like I mentioned, your search history, where you have almost surely typed your own name into there, so that gives a pretty good guess of who you could be on your account, right? And there's also lots of other identifying stuff. I've typed for lots of stuff where I write Utah in there, right? So they can be pretty sure I'm from Utah, even without any of the localization techniques they're doing. Right, there's this thing that if you, Google, if you have, if you have Google Maps on your phone, or even if you just look at where you log in, they can basically track where you are basically every day. Every time you log in, they kind of have a sense of where your location is. And if you have an Android phone, I think they have a lot more information. They kind of know where you are and you drive around. If you stop to the store, or you stop to the house of your mistress, probably none of you have mistresses, but this sort of thing can show up. I've heard a story of, again, I don't know if it's true, but it's a good story. There was some person who was pitching some software to some venture capitalists, and so it was this tracking thing where they could track where you were. This was like 5 years ago when this was still we realized this and say, okay, why don't you put your name into here? They typed his name and it showed him going to some places that were kind of embarrassing, like a mistress's house or something like that. And he got in trouble, but it was a very effective demonstration at the same time. So, so these, there's a lot of information that is being tracked which you might not realize is being tracked. Okay. Okay, so, this started with, this really kicked off with this kind of, this paper and this works, so started by LaTanya Sweeney, this really helped launch this area, and people tried to say, I want to define anonymity, and so the idea was I'm going to have the full data set D, and I'm going to map this to a data set D prime. And D prime should have the property that you shouldn't be able to identify anyone. So you want this to be as detailed as possible, so and not identify. Right, so you don't want to be able to identify any one person in the database. Okay, and so there's kind of a series, and there's kind of maybe a few dozen of these notions of what does it mean to be, what does it mean to anonymize this data, and I'm going to kind of just describe the most popular three of these. So the first one's called K-anonymity. Okay, and so the three will kind of build on each other. So each of them is going to, the second one, L diversity, and then T closeness, are going to include K-anonymity as a property it must maintain. And the idea is that you've got this, you've got this categorical data about people. Maybe it's what movies they've watched, it's their birth year and their gender and their zip code, something like this. And what you want is that no group which is going to be, let's say S, which will be a subset of D, will have be the only ones with some specific traits, and the size of S is less than K. Okay, so that means if I look at the specific traits, I look at the gender, the zip code, and the birth year, I need to have at least K people, let's say K is 5 or 10 people, that have the exact same gender, birth year, and zip code. Okay, now if I don't have that, then what I need to do is I need to withhold, say, the zip code for those people. Right, so then I say I'll withhold the zip code, or I'll withhold the birth year of these people, so that every group I can only identify someone down to a group of possibly K people, which are these identifiable traits, which are these public traits. So based on the public traits, there's no group of size less than K which can be specifically identified. Right, so this means instead of being able to specifically identify the governor, and then their health records are what's tied to these by these traits, these are the things which should be somehow kind of aren't linked to anything public, then I should say, well, I don't know which of these 5 medical files or 10 medical files is the governor's. It's one of these 5. Right? So instead of being able to send the governor, say, this is clearly the governor's medical file and send it to them, I can say, well, it's one of these 5, and you send all 5 of them. That's a little bit less kind of, it seems like less of a big deal. right? Okay, and so this was the first technique, and then there was a big series of algorithms to quickly create the largest data set D prime, which satisfied these traits. Okay, so I want to, how many categories can I keep and still satisfy this property? Okay, so what can you imagine is a possible problem with this? Yeah.
Well, if you're trying to make it so that the data points are less distinct, then by doing this anonymity thing, you're also like losing like very significant information that would like differentiate specific points.
Sure, right. So if you may not have you might get a bunch of these missing data values, and then this prohibits you from doing some useful data mining on it. Yeah. So so this is definitely an issue, but you know, let's say there's like a state law that says that you need to anonymize the data in some secure way. And actually, this medical record anonymization is pretty close to this anonymity model, right? So they say you can release or you can have researchers work with the data after it's gone through some sort of anonymization. There was a group in here who got data from a startup a couple years ago, and they had it, and they realized that for every person they had 100 other data points that had the exact same like geolocation and time period. Right? They took a bunch of data and they rounded every group of 100 onto a single point in a single point time and space, and so they have anonymized it in this way. And then they said, okay, here's the data, now go do data mining. Right, so they said, I want to do this as best possible so I can do data mining. Let's hope that I can still do data mining. But they didn't really answer what can you still find here. Yeah, so that's one point. But we're more worried about the privacy. And there's still some privacy issues with this. Yep.
If you get down to a certain set of people and these K people are missing the zip code,
Yeah.
then you know at the very least they had different zip codes. You don't know which zip codes they had, but you can guess that they must have been different. Whereas if they were all the same, then you would still have the zip code information.
Yeah. So you can learn some of this information from it, but it doesn't help you like localize a person anymore. So.
I guess this new data set would not be organized according to zip code. You'll never know which K people have the same zip code, right?
Well, so sometimes you'll keep the zip codes and you'll throw away gender or something like that.
Are you saying we're creating S without certain fields, like for every different S?
Yes.
So like for these S, we get rid of the zip code. For these S, we get rid of the gender.
So typically what they do is they'll either not release the zip code, or maybe they'll group together sets of 2 zip codes together and they say it's in the zip code group. Or they'll say it's in this age group, you're not born in 1970, but you're born in 1970 to 1975. Right? They're able to do that. So they kind of blur, they kind of make it less specific so that the groups are larger sizes. And there are various ways to kind of do this depending on what the categories mean. But I'm worried about, like, this is actually does not really anonymize it because of there are certain privacy things which are still leaked from this definition. Back there, or?
No, it just seems like you're just reducing how much you can know about any individual, but you're still putting them in groups. So in some sense, you're still being categorized into some subset of the entire data set, but that doesn't mean that you're unknown. You're just being lumped into some particular group.
Yes. So good. So this is the root of the issue, right? So what happens if the governor it's one of 5 medical records, but all of those people with the medical records have some form of cancer, right? If all of them have brain cancer, right? Then then okay, I don't know what brain cancer the governor has, but they have brain cancer, so I haven't hidden that trait, right? So it's lumped in a group, but those groups may have trait which everyone in that group has this trait that is somehow embarrassing, right? So I broke it down to groups, but it doesn't mean that I've hidden information. So then there's this next level which tried to address this, so-called L diversity, and it said that there are L well separated, and this is some technical definition, but think of this as L. So L different traits. Let's say there are either no cancer or there are different types of cancers that someone could have. And so if there are L well-separated traits, that each group, let's say S, has at least 2 of these traits. So at least one person in the group must not have cancer, for instance, right? So that way you can't say, okay, the governor must have cancer or some other, so maybe like potentially terminal disease, right? Where as long as some person does not have one of those traits, then you can't know that for sure, right? And so this was this measure of L diversity, and so this adds another layer of protection, right? But this doesn't quite solve it, because let's say that there are 5 people in the group and 4 of them have cancer, then you're still pretty sure there's a pretty good chance that the governor has cancer. Just because they have one of each trait doesn't quite solve this. So then there's a third version, T closeness. Okay. So and actually Suresh was one of the people who kind of came up with this formulation. And this was basically saying that of the hidden traits, they must be T close to the distribution of the full population. So if you look at the full data set and you say, okay, so 10% of people have cancer, and T is 10%, then you say, okay, so then I can't have more than 20% of any subgroup to have cancer, because that would indicate it's an elevated chance of having cancer if I've identified this subgroup. Okay, and so there's some, you can't match it exactly, but you can add some parameter here. Yeah.
How do you select your hidden traits?
Yeah, so this is tricky, right? So this assumes that you know that certain traits are somehow sensitive and certain traits you think are not. And it's not always clear which traits are sensitive and which traits are not sensitive, right? So in order for this to work, you somehow need to, you somehow need to designate this. So like with health records, it's thought of that age and zip code are generally not sensitive things, but if people have worked with these for your projects, you get these different codes, medical codes when you go in. Which codes you are under your account might be something that's going to be sensitive. Now maybe your birth year is going to be sensitive. Maybe something like your height is so it's also sensitive, right? What if I want to just release the height and weight of the population? It seems like this might not be that sensitive. But let's give, and I want to give another example here. So let's say that I somehow figure out that Stallone has the average height of a man in New Jersey. So let's say that his health records are in New Jersey, and I don't know what his height is, but it's in a category that's really close to the population of New Jersey, and so I've identified that he has the same height as the average person inside New Jersey. Now, if you've looked on the web about this, at some point when I was kind of creating these notes one year, I was looking up this on the web. Apparently, there's a controversy of so how tall is like Sylvester Stallone. There are pictures where they try and identify this, where they show him standing next to people where they have a known height, and they show, okay, he's wearing boots in this that give him a lift. There's questions about, there are pictures before a certain date and after a date, and he may have had surgery so that he's actually gotten taller by extending his leg bones or something like that. There's all sorts of a controversy about this, and apparently he's not like, I believe he's shorter than I am, but he'd like to be known as someone who's a bigger, taller guy. I believe he's like significantly shorter than I am. Okay, and so he would like to keep that information secret. Okay, and it seems like he may have had some personnel like go and try and remove information from the web of how tall he actually is. So this is a trait, his height, which he wants to keep private. Okay, but you can imagine releasing something like, okay, he matches the average height of a man in someone like New Jersey, and then you can say a separate survey, you know, in New Jersey, that the average height might be something like 5'8". Okay, he might actually be 5'6", but let's say this is 5'8". This would reveal his height. Okay, so there's this information, you don't know what can be linked with other information which is available online. There are these other surveys which may have to do with kind of medical rates, which might leak information. So it's hard to tell what is really a private trait and what is not a private trait. But these other notions, they kind of needed you to do that in order for it to work. Okay? So I want to tell, oh, yeah.
So does this lend itself to the idea that all traits are sensitive?
Maybe, yeah. So it's like hard to know what is and is not a private kind of another story that kind of is kind of touching on this. So who heard of the Netflix prize? Okay, so this was around 2006. Netflix released this really awesome data set, and they had a prize for $1 million. And the idea was that they released this data set of movies with a user ID, but it was supposedly anonymized. And the only data it had was for every person who watched a movie, and they gave a grade to the movie and the date of the grade that they gave on the movie. Okay? And they wanted to use this to predict which other movies this user would also like. And Netflix had their own internal algorithm, but they said, we'd like researchers to try and do better than our algorithm. So they had this one data set D that they had this in the grade, and then they had another data set you'd like to make a prediction, where they had the same user ID, the movie, and then the date of the grade, but they didn't tell you what the grade was. Right? So that you're supposed to predict what the grade was. It was like 1 through 5 stars, something like that, whatever. Now they do it, I don't rate movies anymore on Netflix. I guess you just do a thumb up and a thumb down now, but they do it by, did you actually watch a movie? That's a sign that you probably liked it. If you turned it on for 5 minutes and you realized this was horrible, you probably didn't like it, right? So they're still doing something like this to make predictions. And this was back when they were just sending DVDs in the mail, right? So this was ancient times ago, right? Okay. And so then they had another data set, D3, which they had internal, and this is what they used to kind of evaluate these grades, right? And so there's this big challenge, and there are these teams who spend huge amounts of like, oh yeah, and if you get a certain improvement over there, you would get $1 million. It's like a 10% improvement, which was actually a lot. And so there's lots of cool research that happened here. There were tons of research groups who worked on this. The winning group, I think, there was a group from Bell Labs that I think Maine led it, but these groups merged together. And I think in the very last day, they merged together with another group from Canada, I forget where. And I think they just missed the threshold, but I think they still gave them, maybe not $1 million, but almost some pretty good prize for this. And the cool research was how to do like ensembles of different classifiers. And it really came out of this work that ensemble methods were super powerful, that they would build all these different training methods and learn how to kind of use them all together to improve upon each other. And so that's why these groups were combining together, because they both had their own classifiers, and then they could build ensembles across them. So these groups merged together to become these super groups. So some really cool research came out of this. Okay, but at the same time, a lot of the people this was back in 2006, and this was largely people who really liked movies a lot and would rate these movies a lot. These people also tended to rate movies on IMDB. Okay, in IMDB you have a user ID and you have a timestamp when you rated the movie, and maybe you'd rate the movie similar ways. And the user ID was often kind of maybe linked to an email address, and you can often figure out who was the IMDb user. It may have technically been anonymous, but it wasn't as anonymous as this Netflix stuff.
Jaccard similarity comes into play, right?
Yeah, you could do stuff like Jaccard similarity. You could figure out like what movies they rated similar, and also the timestamps when they watched them. You usually rated a movie as soon as you watched them, so the timestamps would line up really well. So there was a group that showed that you could very closely, the people who rated them on Netflix and IMDb, you could almost 100% link who rated which movies and link up the Netflix users with the users on IMDb. And you can almost identify like really closely who was, so who these data points were in the Netflix. Okay, and so this actually, and so some people might have watched stuff on Netflix but not rated on IMDb because they were embarrassed to rate it. Maybe it was some, maybe it was a silly comedy movie or a rom-com, or maybe it was some other movie you didn't want people to know you were watching. You did it on Netflix, but you didn't go on IMDb and rate this as being this was a really good movie. I'll leave up to your imagination what that might be. Okay, so some people were upset about this, and there was a class action lawsuit against Netflix because of this. It was later dropped, so Netflix didn't do this, but so like Netflix had proposed a sequel to this where they were going to do another thing in 2010. It would have been a huge, even bigger data set, right? They were going to release this. They had announced it about the start date, and they were going to do this. And because of this class action lawsuit, I believe that was the main impetus for it. They dropped this, and they ended up not releasing this data set. Okay, and so like between 2006 and 2010, this was kind of the golden age of being able to go to those internet companies as a researcher and say, can you let me see some data? I want to try some algorithms out of it. And often they would do that, and then this kind of stopped. Okay, and probably for good reason, right? Now, you see like you heard in the news on Facebook, this still happens, and they'll still let you do this, but it's much more restrictive than it was in this period, right? Netflix gave out this huge amount of their data, and they were prepared to do this again. And other companies were doing the same thing if you knew the right person to ask and they kind of trusted you. Now there are ways you can do it, but it's often much less data. Apparently Facebook wasn't so careful about this, but like Twitter, you can, I believe there are ways to mine a lot of data from Twitter, for instance, because it's all out there, but I think those tweets are kind of, they're published out there, right? There's nothing specifically hidden about that. But like the streams you can get are more specific if you try and do queries with respect to a keyword or something like that. Okay, and you have to kind of go through a much more trust process to get more data than that. And that's usually at most only 10% of their data, unless you're actually working inside the company. Okay? So, you know, it's hard to know. This was the data they were studying that was useful to do any sort of analysis with is exactly the data that should have remained hidden, right? So it's, you know, it was hard to know what this was going on. And so at this point after here, there's some data sets on the web, but they're extremely clean, right? Or they just do a new simulation of the data and they say, okay, this kind of looks like our data. We believe this looks close enough to our data. But it's not really the real data anymore, and you never really know if it really matches what's really out there. And some things that they just won't release at all, they think is too sensitive. Okay. So, and this kind of, this k-anonymity and those derivatives of that, I mean, it kind of realized that with other data sets, you could often recover this irregardless of the way you try to anonymize this data. Now, health records in certain places are still released using some of these standards, but you often have to go through like an approval background check process in order to get those. Okay, so around this time, there was a new kind of approach that came out to how to release data anonymously or interact with it in a way where you can still do data mining on it, but to protect individual elements. Okay, and this is a new notion called differential privacy. Okay, and so the idea of differential privacy is you have some data set, I'll call them D1, and this is the true data. And then there's another data set, D2, which is, this is either released or in other ways you're given access to it, and we'll discuss these other ways. Somehow D1 and D2 are going to be close. So they should be close in the specific sense in that I want to be able to run data mining and machine learning operations on these data sets, and the results should be similar. Okay, and I'll describe what that means, or maybe do database queries of it. Okay, these results should be similar. But I'm also protect individual of these data points. Okay, I want to protect the individual data points as well. Okay, and so like this is kind of the goal we've been talking about it, and the difference is they formulated this in a probabilistic way. They say that I want to not be able to probabilistically distinguish between these two essentially data points in these individual data sets. Or more generally, these certain types of queries on the data set, I don't want to be able to distinguish them up with some probability up to some amount of error. Okay, so, and if I can do those queries with some amount of error, I can often get approximately good data mining and machine learning results on D2, but I won't know for sure if any individual kind of elements are actually in D1, because D1 and D2 might be the same in a certain thing, but they might be different. Okay, so this is kind of trying to, all these issues that like, I presented this whole lecture kind of knowing that this is kind of the whole issue, but when people are coming up with these other forms of anonymity, they didn't really understand that this is kind of the critical issue. Okay, so this is kind of a way to formally define this guarantee with this release of data, and then there are algorithms that try and make D1 and D2 as close together as possible from a data mining sense while satisfying these indistinguishability guarantees. Okay? And so I'll try and define this. I'll try and define this generally, and it might not quite make sense, and then I'll try and give some examples that'll try and make it more clear. Okay, it's a little bit, takes a little bit to wrap your head around that this is the right notion. Okay, so think of, so we're going to say that, so you're going to have certain some queries, in some set of queries you can ask of D2 or of D1, and you have some property R. And so, for instance, it's this property is like I want to ask how many people in the class are older than 40 years old, okay, or are older than 30 years old. That would be the query, right? The query would return all the people older than 40 years old. So the query of D1 might return the ages of class, and R would return the number older than 30. Okay? So something kind of like this. This is an example. Okay, and then the guarantee that I want is that for any set of queries and properties, that the probability that the query on D1 is in R, or over some class of queries and properties, and that the query on D2 is in R. So, right, so that so if, say the number of people older than 30 is like there are 10 people older than 30 in the class, right? So the probability that's true on D1 and D2, I'm going to randomize this somehow. I want this to be close to each other. And you say this is e to the power, this is the same thing as e to the power epsilon, and this is usually how they write it, but you think of this as 1 plus epsilon, right? So these are always going to be close, right? So this will be the notion that defining a set of queries and a set of questions of properties you can ask, I want these to always probabilistically be close. So I want them to always be within a 1 plus epsilon factor. So set epsilon to be like 10%, so they're always within 10% of each other. Okay, so I would say this way of presenting D1 and D2, these are epsilon. This implies that they are D1 and D2 are epsilon differentially so private. Okay, and I'm only allowed to ask these sort of queries. Yeah.
Is it always possible to find on any data set?
Well, it depends on the class of queries and the class of properties that you're allowed to ask.
Because
Okay, and I'll give some examples of when it's true.
right, because you would like D2 to be much smaller than D1. That's the idea.
Well, I want D1 and D2 to essentially be in order to preserve the anonymity of people, I want them to be as far away from each other as possible. I want to somehow, the simplest way to do this is going to be to add noise to D1, and that's going to get you D2. Okay? And so if I add enough noise, then I don't know anything in D1 by looking at D2 because I added a lot of noise. But I want this to still hold because something like this will still allow me to do some data mining. I can still ask, right, so if the number of, so let's say I allow 10% error, I want to know the number of people, is the number of people in the class over 30, is that more than 10 people? Right, and so let's say I'm going to give an answer and I return the answer is 12. Right, the number of people over 30 is 12, but I've added 10% error, so if I know everyone's age except your age, and I know the answer to the question is, I got an answer is 12. So let's say I don't know. I know there are 11 other people in the class who have age 30 or more. I still don't know if you're 30 or more, right? Because I've added noise to it so that I'm off by 10% error. So I don't know if any individual is 30 or more because I know the queries are going to be, I've added enough noise that I could have changed anyone's individual. I can't, even if I know everything except your data point, I can't distinguish them.
Wouldn't you be able to distinguish them with like a very high probability though, unless your error is very high? So you're putting like privacy and the accuracy you're getting at like distinct odds with each other, right?
Yeah, so I'm guaranteeing that a query. So I'm going to release the data set, and I'm basically going to tell you the way I'm randomly choosing D1 from D2. Sometimes there are deterministic ways to do this too, but there's ways you can't reveal stuff. But let's say I'm randomly adding noise to it. I'm going to tell you I'm randomly adding noise to D1, or to the answer to all the questions. Okay? And I'm going to guarantee this property, which means that you can still do some reasonable data mining on it. But then because I added noise, you don't know, like you only know probabilistically if someone, like I don't know for sure, right? Maybe it is, maybe it's not, right? And but it won't. For certain things, it might be with high probability that you can recover, but hopefully you can't. And you want to try and balance these two aspects. Yeah.
So this data set D1 for the query, I'm wondering this epsilon factor, to get that noise that you're talking about, will that epsilon factor be applied to, can you apply it to the query, or can you apply it to the D1 to get that noise?
Yeah, so there are two versions of this, and that was the next thing I was going to explain. You have a question first?
Does R have to be the same?
Yeah, so R usually comes from a class of questions you can ask, a class of traits. So for instance, you can ask I can ask the number of people for any, for any age group. Those are the allowable questions I can ask, right? Where I return the number of people in some, I can return the number of people's age, but I'm only asked how many people are this age or above.
But I'm just thinking because if you want the same probability, what you're interested in is the distribution of ages. If you don't know the bounds, then you could say how many people are in the oldest 10%, for instance, but you don't know that that's over 30, or you don't know that's over 40. Or like for zip codes, you can have something that indicates geographical similarity, but you don't actually have the zip code itself, but you can still have the same distribution of where people are located, but kind of rescaling everything so that the R's are different, but you get the same probability and you can learn the same information. But you're saying R has to be the same.
Well, usually R comes from some class of queries, and there are lots of different versions of this for different sorts of questions you can ask. So, for instance, there are some versions of this where the queries and properties you can ask have to do with taking a dot product, and it turns out if you allow someone to take enough dot products, you can basically run most machine learning algorithms. Right? You can build most types of classifiers by just asking types of dot products. And so every dot product, you'll return something that's approximately right, but they will ensure that you can't distinguish certain data elements because of the noise process they run through the data, that they run the data on before they allow you to run dot products. So there are lots of different types of queries and kind of and these properties that you can ask these combinations. This like the original definition was set up so D1 and D2 were data, they call databases, which are just like these bit vectors. And then you ask a query that asks for a subset of the bit vectors and said how many 1 bits are in this. And you can return how many 1 bits in certain ranges. And they basically show if you add error to every query, then you'll guarantee this, but because you add error to every query, you never can distinguish individual bits on a single query, because you might get it wrong. Right, so that was the original setup, but people have to figure out how to adapt this to a lot of things within data analysis, and it gets more complicated. And I'll go through a few more examples that'll start getting in that direction, but I won't show you all the way to get to something totally useful. All right, at least not like, I'm not going to show you how to run k-means clustering in a differential private way, for instance.
Just one more question. Are there ever any cases where they can backtrack the anonymity? So you find a really cool finding, but you want more information, so you somehow request to lift that anonymity to audit. Does that ever happen? Have you ever seen that?
I'm sure in the setting of like, so like in governments, this has happened where the government protects the layers of information with different levels of classification. And like if you ask for a warrant for something, then you can go look for more information. I'm guessing this has happened with health records for certain medical emergencies. This has probably happened. I'm not strictly aware of this. I know this has happened with, this is an ongoing thing with the tech companies, right? Let's say someone committed a crime and the police get their iPhone and it's locked. Okay, so they've anonymized the data on the iPhone by locking it in some way, right? And they go to Apple and say, unlock this iPhone for me. And Apple's like, if we do that, like, you know, like we can't do that, right? Is their answer, right? And so they try and not do this. And I know, like with there was this issue there's issues with respect to looking for potential terrorists. There are requests to these tech companies for they identified someone in the U.S. as a potential terrorist, or maybe not in the U.S., and they said, I want access. I know their email address. It's on all your emails on your server. I want access to it. And I think some tech companies were forced to comply with this for national security reasons. And I don't think they were happy about this. And there are various levels of who resisted more and not more in these cases. But this sort of thing happens in these situations. Whether, as a society, this is the right thing to do or not, there are different sides to this issue. I have my opinions on it. Not going to force my opinions on you guys. But, okay. So a lot of these companies now, so a lot of this differential privacy was invented at Microsoft, and Apple's now using some version of this. So now when they store the data, they want to store it in a way where they can ask certain queries and useful for doing the sort of mining revenue, but they don't store the actual data. They store some noisy version of it, kind of as it turned out, and then if someone asks for the information, they're like, well, we don't have the specific information, we just have this noisy version, which is sufficient for us to sell our ads on the platform, but not enough for all this other stuff. That maybe it's encrypted or something like that. Encryption's a whole nother interesting avenue. Like you can encrypt all your email in various ways. Most people don't do it. I don't do it, I'm too lazy. So please don't hack my email. I know there are certain classes where I know people who teach like privacy classes, and they kind of teach their students how to like hack certain stuff, and some of those professors get their emails hacked because the students are like, well, who should I do? I'll impress the professor by hacking his email. Like, no, don't do that. Okay, so so there are two ways two kind of modes that this can work under. So there's this interactive approach where there's a trusted entity with this data set D. Okay, there's a trusted entity, and so basically you could think of D as behind some wall, and basically there's some user who sends in some query, right? Or maybe it's a query and some property that they're trying to ask, and then the entity will send back some answer. This answer here. Okay, so they can store the exact data set here, but then they will send back this plus some noise, right? So the user only sees the answer with the noise, but they're actually storing the full exact data set. And so the noise that you add in order to distinguish these things, this probabilistic part, is put on the result of the queries. Okay? Then there's this other way, there's this non-interactive approach, where you actually you store some data set D2, which is the data set D1 plus this noise. Okay, so D1 is not stored. You only store D2 and it's add noise, and then you might actually publicly release this D2. I might put it on my website for kind of people and researchers and other inquiring people to look at this data set D2. You can do whatever you want with it. It's been noised up in some way, right? And so now I'm not controlling. You can ask as many queries as you want on it, right? And so typically this noise is going to be specifically Laplacian noise. And so this Laplacian noise, so a Laplacian noise is kind of like Gaussian noise. It's C to the e to the power minus epsilon. Where Gaussian noise was e to the power negative something squared, Laplacian is just e to the absolute value of the epsilon. Or in this case, it's always some positive value. Right? So whereas this Laplacian noise looks kind of like this. Right? So if I return a count, I return 10 and I have Laplacian noise, where say the variance, is epsilon or is 10, right? Then it's going to be off by roughly 1, right? Or off by roughly epsilon, or if it's so whereas if I had Gaussian noise instead, Gaussian looks like this. This is Gaussian. It's kind of smoother. It's not so flat at top, but the Laplacian noise is kind of pointy. Okay, so Laplacian noise is used because the math works out nicely. Okay. Okay, and so in this mode, you can release the whole data set. In the interactive mode, you can add noise under the queries. right? So this example I kind of gave before with the database, and we'll walk through that a little bit more carefully soon. If I can add noise onto every time someone asks a query for a range, I can add a new noise. Now the advantage of that is that I can just add random noise every time, but I can also keep track of what information I've leaked, okay, in an interactive setting. So the database can say, you know, someone has asked these queries and they're zeroing in on one data point. And if they keep asking the same query over and over again, and I keep returning noise, but it's IID noise, then they can just take the average of the results and they can learn, and they can learn what the true value is pretty accurately. So what they can do instead is they can make sure that the noise is going to be correlated in some way, so that I preserve that these that any query looks like Laplacian noise, but two similar queries must be correlated. And it prevents these attacks where you repeatedly ask queries over and over again. Now it needs to keep track of all this information, and sometimes that's expensive to do, but people have developed algorithms to do this, to figure out how to do this, yeah.
What's the advantage of using the interactive approach then? Because you have to do all that overhead. Couldn't you just do...
Well, often I can give the same protections with less noise in the interactive approach. Yeah, so I'm able to do the same protections with less noise. Yeah. Right. Okay, so let's start with kind of a simple example where, okay, so I'm going to have one, so I'm going to have two, okay, so D is going to be my true true data set, and this will be Sly Stallone's his height in inches. Okay? And so now I'm going to consider creating two data sets, D1 and D2, where each of them is plus some so some Laplacian noise, and let's see if so plus some epsilon Laplacian noise, and this is plus some epsilon Laplacian noise. Okay, and so I'm going to think about doing two of these, and I'm going to give the users one of these data sets, right? So so let's say that the D1 is going to be 67, and D2 is 67, and D1 is 68, right, in inches. So this is 5'8", and this is it's 5'7", and so now let's say I want to determine the probability that D1 is going to be the answer I get from this. So this is the result of like the queries are these numbers I get. So the query on D1 is 68, or the query on D2 is 67, and I want to know the probability that this is greater than 70, that the true data set is right this way. So the probability that D is greater than 70 given D1, right? And the probability that D is greater than 70 given D2, right? So the probability that the true height, he's taller than 5'10", 70 inches, is greater than, probably is greater than 5'10", given the observation D1 or given the observation D2. I know I got one of them. I know they're given with noise, right? And so the probability given D1 is going to be approximately e to the minus 2 epsilon. Okay, because It's Laplacian noise. And so I was given D1, and the distance is 2 from 70. And so the probability with Laplacian noise is e to the minus 2 epsilon. This turns out to be the right probability. And with given a query of 67, it's e to the minus epsilon, 3 epsilon. And if I look at the ratio of these two things, the ratio of these is going to be exactly e to the minus e to the minus epsilon, which is going to be roughly 1 minus epsilon.
Should be positive epsilon.
Yeah.
Yes. That's what it said in my notes, but I doubt inclusive. Yeah. Okay, so the ratio of these two things is e to the epsilon, which is approximately 1 plus epsilon. So given these two releases, and I know the mechanism I was given D1 or D2, the probability that the true, that he was actually 70 inches or taller is going to be, independent of which one I get, is going to be off by 1 plus epsilon. Now, maybe I released and it was actually 71, maybe I released and it was actually 65. I could release something different, but if I released things that were off by 1, then the probability of him being less than 70 is within 1 plus epsilon. So I can still mine this, and the mechanism I've done this is I've added this Laplacian noise. So I can still predict the probability that his height is greater than 70 inches, right, up to probability 1 plus epsilon factor. Okay? But I've done it by adding this noise. So I've added noise so I don't know the true height. Okay, so the privacy guarantee is that I've released it with this noise so I don't actually know the true height. And the guarantee is that I can still ask this question, and independent of what I was given, I'm still off by a 1 plus epsilon factor if the height, if I fake the height off by 1, this question here. Okay, so there's some sort of guarantee in the analysis I can give between two return answers that are off by 1. And in the process, I've given some anonymity by adding Laplacian noise to the actual the actual value. Okay. Yeah.
So this will prevent you from being able to like discern exactly that his height is 68 inches, but wouldn't it still tell you that his height is no more than like 69 inches?
Yeah, so I'm not, well, it's,
Or
like it's still, like I still know, I haven't added that much noise to it, so I still have a pretty good sense that it's very unlikely he's greater than 70 inches.
it'll give you like some balance, right?
Yeah. So I still know he's very unlikely to be less than 70 inches, and I can deduce that by looking on the internet at all the photos and so forth. Anyways, but do I know his exact height? Maybe, this release of information has protected it in some way, right? Up to the same level of uncertainty I have in this set of these photos online. So it's kind of, if I want to have more protection, I want to add more Laplacian noise. If I add more Laplacian noise to it, then I would have less accuracy in the probability he's greater than 70 inches. So the more privacy I preserve by adding more noise, the less accurate my data mining query is going to be. Right? And so this is sort of trade-off that you can get in. It's trying to study how good can I make these trade-offs. Yeah.
So like for the Netflix challenge, just that data set, with the noise they add to that, would they be adding noise to each of the individual attributes on each of the current data points, or would it be adding new data points that are like noises off the mean? Or like what's the most common practice for that?
Yeah, so so that's kind of tricky in that, like, it's a different sort of data than this, right? So I have to do something like, what's more revealing is, did I watch a movie or not? Less so than what ranking did I give the movie? So what you would probably allow, and this would be more like this database version of the question, which if you look at the notes, I go through that a little bit more detail. I'll probably run out of time here. But what you can do is you can ask queries of how many movies did they watch in this family of movies, right? And this is something you can do with this interactive approach, is the typical way you would, the simplest way this is formulated. And so then you ask, did they watch this? How many of this type of movie did they watch? How many romantic comedies did they watch in this time period? And they'd return the answer with notes, instead of telling you exactly which ones they answered in. So maybe they return that with noise and also your average rating on those movies. And this might be sufficient for data mining anyways, because maybe you say all these romantic comedies roughly count. It doesn't matter which one they watched, as long as they know, okay, if you watched 30 romantic comedies last year, you probably like romantic comedies, right? 30 or 31, but I don't know if you specifically watched Sleepless in Seattle, that sort of stuff. And maybe that's okay to release, maybe that's not. I don't know. These are not easy questions. But the differential privacy provides some formal notion of, if you can add this sort of noise to queries and still do this analysis. It's not necessarily guaranteeing that you can't use side channel information attacks to recover something, but it's saying, well, I'm only going to return certain things with noise. So the certain questions you're answering, you're only going to get up to some resolution. So it can prevent some leakage of data, and you can still definitely do some data mining with it. But it may not be, if you really want to protect it, you may need to add a lot of noise. And it's up to you to decide what's a tolerable amount of noise. As a kind of, hopefully at some point a lot of you'll be working in these companies where you'll be faced with these issues, and there's no easy answer there, but I hope you'll think about kind of these sort of answers, right? These sort of problematic issues that could happen, right? And this might also explain, when you actually get data from someplace, why you don't get the exact data, or why it's been rounded to something, or why it looks, it's the noise. Someone said, I added noise in a certain way, and you're like, well, why did you do that? Well, this is probably why, right? Okay. And it doesn't necessarily solve all the de-anonymization issues either, but it's a bit more formal, and some people have proven some things about certain things you can't recover based on this leak of information. Whereas with the anonymity-based approaches, there was never any really attempt to formalize what was and was not leaked. Okay, so I think we've run out of time today. Turn in your homeworks by next Monday, and we'll start on markup chains and graphs.